I've just gone back to look at the Mobius strip. So this is a 3-flip Mobius strip. You know, it's just a strip of paper with 3 twists so that the one edge attaches back to its opposite edge, so it doesn't have a boundary. It only has one surface. So if you start here and go west, you end up back here after you convolute it. So when you add a cut, you add a surface. So you can see that when you cut it down the middle, here's one surface, and here's the other surface. It's just weird. So here's it dissected. So it goes from having 3 flips and 1 boundary to having 8 twists and 2 edges. You can see there's a trefoil knot there. So it's 2n plus 1. So 3 twists times by 2 is 6 plus 1. So 2n plus 2 is the number of twists afterwards, right? So 3 twists times by 2 is 6 plus 2 is 8. So there's 8 twists in this with a trefoil knot and 2 edges now. So then you can see how I want to, like if you let it cross itself right here and put a half snip, this will pass through this this boundary, and you can see how it wants to go in little snips. So you can see how if you add like 6 crossings, you get like a knot. That will be called a frame knot. So here's one of the knots that I found. I didn't name it after myself, but I called it the möbius Lorenz knot because the topology of this knot, when there's about 150 different knots, this is with the topology of the Lorenz attractor for its phase-space diagram, and it's beautiful. So I drew the knot diagram, the knot notation. I think this is Conway knot notation. You can see we go +1, -1, -2, -3, -4, +4, +5, +2. You know, you can see what we're doing there. So I was trying to find ways to permutate the knot notation to find all the possible knots, because there's only so many possible knots. Like this manifold can only be permutated to make so many knots. And I just started looking again at what I remember about the algorithms I was working on. I still can't crack it. So it's going back in the bin. I just can't spend another few hundred hours reading topology and knot theory to figure this out. Now one day I'll find the equation that tells me how many different knots there are. Because, hear me out, when you apply that equation to one twist, there's only 4 different knots. When you apply it to 3 different twists, there's X number of knots. You apply it to 5 different twists, it should be definitive. And I believe that there will be an algebraic equation that will tell me how many knots are possible. It's a beautiful problem I'm working on.